Okay, it's my pleasure to introduce Athanase Papadopoulos from Stanford University, and he will speak about arithmetic on Teichmuller space.
Exactly. Yeah, something. Thank you very much. Yeah, but I prefer like this because I wanted to go step by step and not page by page. You see?
But why not to say extreme?
How do I Here?
Click on the text itself. Okay. Double click on
Okay, thank you. So, yeah, I would like to thank Sergey and Evgeny and Vladimir for this invitation to this city, which I know very much. In fact, I was coming every year, almost every year, to Russia during the whole period where Vladimir was not coming. During 20 years, he was, for some reason, in fact, he didn't want to come. And I was, and every day after this, I was discussing with him. He was recommending people to see, he was recommending the places and so on. And so thank you for this. And I have to mention also that my university became a reasonable and very good center, I think, of quantum topology in France. And this is because of Vladimir. And not only he founded this center, but he also, part of this is that several Russians used to come every year. Nathan came 3 consecutive years, and all of you, in fact, I know you from there, so also thank you for this. So as I said, I'm not involved in this quantum topology subject, but I work on geometry, more classical geometry, and it's so I want to talk to you, of course, about something I know and not about quantum topology. And the first part, I made a talk in two parts. The first part is some notes on the origin of this subject. It's always good to remember how the subject started and who are the founders of this subject. So, yeah, so this is Riemann, the origin of everything. Everything I'm working on is Riemann. This is a picture of him at the age of 37. In fact, he died 2 years after this. But I want this to be smaller.
Do you know what it was? What was this? Why did I so young?
I would say a few words about this, but I want this to be smaller. Minus. Okay. Okay, thank you. Okay, so in fact, he introduced the concept of Riemann surfaces. It's this subject, which is, our main subject here. I will tell you a little bit more about this. Here, he introduced an equivalence relation between Riemann surfaces. For him, it was in terms of birational equivalence. Today, we describe a little bit differently. The people who are not doing algebraic geometry have another way of describing this equivalence relation. And then the important thing is that he stated that the number of moduli for a closed surface of genus G is 3G minus 3. And this was a very strong statement, a very mysterious statement, because there was, at that time, as you know, there was no notion of manifold, there was no notion of high-dimensional complex structure. In fact, he talked about Riemann surfaces, but there was nothing at all as complex spaces of high dimension. So this 3G minus 3 had no rigorous meaning, in fact. And the work which was done, say, during 80 years after Riemann stated this, was to give a meaning to this count here, 3G minus 3. And several people were involved. I want to mention the main people. The main references for this is Riemann's thesis, which contains the basis of the theory. I will state that one of the sentences here. And then a memoir which he wrote 6 years after the memoir on abelian functions. Of course, all this is in German. Where he came back to the definition of Riemann surfaces. Did I? Yeah, okay, so I will tell you more. So this is the introduction of Riemann surfaces. So the variables x and y, these are, so we must understand as z equals x plus iy. These are the real variables of the complex plane. We restrict the variables to a finite domain by considering as the locus of the point O no longer the plane itself, but a surface which is spread over the plane. So he was thinking here like a cover, a branched cover of the plane. And we admit the possibility that the locus of the point O is covering the same part of the plane several times. This is the beginning of Riemann surfaces. And then, well, this thesis here contains, you cannot, the people who don't know cannot imagine how many notions it contains. So it contains, this thesis contains the first uniformization theorem, which we call the Riemann mapping theorem. It contains ideas about potential theory. He introduced these ideas in the theory of Riemann surfaces. In fact, he used the Dirichlet principle in this proof of the uniformization theorem. That's a very interesting story, in fact, here, which I don't want to go into, but it is Hilbert in 1912 that made this use rigorous, and that it was after 60 years that people recognized that Riemann's method was sound, in fact. And then you have the first version of the Riemann-Roch theorem. You have all the topological concepts, all the basic topological concepts like connectedness, interconnectedness, degree of connectivity, covering the genus of a surface. Everything here appears for the first time in Riemann's thesis. And then many other things, abelian integrals, the characterization of abelian integrals by the period matrices, and so on. So this is part of Riemann's thesis, and Riemann's thesis is part of his major work. And I want to show you two pictures here. In fact, this is a picture from Riemann's thesis. This is a familiar picture of a Riemann surface, and here he cuts. Here are two cuts to make it simply connected. He's counting the degree of connectivity, and he's doing many other things on this Riemann surface. So I wanted to compare this from this picture, which was in a famous French book on Riemann surfaces by Appel and Boursat, where they explain Riemann's ideas and Riemann surfaces. But for many years after Riemann, everybody imagined that a Riemann surface must be something embedded in free space, and they try to imagine how these leaves cross each other. You see it's saying that okay, it is embedded, but you must not see these cross curves and things like so they could not. Riemann imagined the abstract concept of a Riemann surface without any embedding in free space, but for years and years after him, people could not imagine this. They were still thinking of Riemann surfaces as embedded in free space. Okay, so I don't want to go too much into this historical introduction, but I want to mention all these people, in fact. So I said that the major problem here was to give a precise meaning to this 3G minus 3 here. And this involved a lot of people, and I made a list here. This is, I mean, the major mathematicians are Poincaré and Klein after Riemann, and this picture here. This picture is taken from the correspondence, a letter from Klein to Poincaré. So they introduced the notion of group in this theory and group actions, and they both realize that Riemann surfaces you can think of them as Fuchsian groups, as groups. I mean, this equivalence class here, this 3G minus 3, they tried to count it as a number of, there was no notion of dimension, but as the number of parameters of parametrizing Fuchsian groups. And then there were all these people, Brouwer, Weitz, Siegel, Torelli, Teichmuller, André Weil, Grothendieck, Mumford, Delin. So here, I wrote a list, and in fact, starting from Weil, all these people are Fields medalists working on, and for their work related to moduli, the problem of moduli, which started in Riemann, and some of them are not very well known. You know, for instance, Brouwer, people do not know his work on this. His work in this field is very, very poorly known. And in fact, he introduced his theorem of invariance of domain because Klein and Poincaré, in their uniformization theorem, which was also related to this moduli problem, used some map, you know, and they tried to prove that this map is a homeomorphism onto its image. And the map, the spaces which were involved were not, they had singularities. And one of these spaces, one of the two spaces, was what we call a Riemann moduli space. They worked on Riemann moduli space. They tried to apply this, showing that the map is a homeomorphism using what we call now the Brouwer invariance of domain. And Brouwer was the first one to point out that this was not possible to use this theorem because of the singularities. And then he proved his famous invariance of domain, which was used later on, which was used in particular by Teichmuller, which I want to mention. And here I have a picture of the last person on the list, finally a woman. Mariam Yezafani, whose work also is on moduli and Teichmuller spaces. So finally, there's a woman in this list. And now I want to end, because this is complicated, so I want to write it, I want to read it from my notes here and not to write it on the board, and then I use a blackboard. So this is from Teichmuller's paper, 1954, this paper called Variable Riemann Surfaces. So this is one definition of what is called today the Teichmuller space. You know, there are several ways to define this space. At least three very common ways, and this is another way which people do not know about. It's really different, and it's more interesting, and I will tell you why. So the theorem says there exists, so I'm translating, in fact, a friend of mine translated from the German, but this is exactly what Teichmuller says. So the theorem is that there exists an essentially unique, globally analytic family of topologically determined Riemann surfaces H of C, where C runs over a tau-dimensional complex analytic manifold C, such that for any topologically determined Riemann surface H of genus G, there is one and only one C, such that the Riemann surface H is conformally equivalent to an H of C, and such that the family H of C satisfies the following universal property. If H of B is any globally analytic family of topologically determined Riemann surfaces with base B, then there is a holomorphic map F from B to C, such that the family H of P is the pullback by F of the family H of C. So this is, I mean, you have to read this several times and to have a piece of paper in order to understand this. But the meaning, I mean, the main thing here, there's this manifold C. The main thing is that, okay, for the first time, in fact, there's this mention of a tau-dimensional complex analytic manifold, and tau is this 3G minus 3. And this tau now has a meaning of a complex analytic, of the dimension of a complex analytic manifold. And so, this C, which is what we call today Teichmuller space, is defined by some universal property. And the theorem says that there exists a space, C, complex dimension 3G minus 3, which satisfies the following universal property. So above this C, there is this fiber bundle, which is called today the Teichmuller universal curve. And this space C, together which is its universal curve, the universal curve is a fiber bundle where each fiber over any point, over some point, is a Riemann surface which is represented by that point. You know, I told you that this space which Riemann defined is a space of equivalence classes of Riemann surfaces. And there's this fiber bundle over it, and then this fiber bundle together with the base are defined by a universal property. The universal property is here. It says that every time you have another fiber bundle here with another base B, then this fiber bundle here is obtained as the pullback of this universal one. This is, well, and some words here for those who know, when he says that the topologically determined Riemann surface, this is what we mean today by a marked Riemann surface. And this is interesting, I mean, this is very interesting because this marking removes the singular points of the moduli space of Riemann surfaces. And somewhere after this, Teichmuller says, until now people talked about this dimension and tried to compute it, but they didn't know what they are talking about, because the dimension, you see, after Riemann and until Teichmuller, this dimension, they were counting parameters again, and at some point, in fact, in between, there came this example of contour of a bijection between R and R square, or R and Rn, and then he showed that counting parameters does not lead to anything, because all these spaces, I mean, you cannot say that just by counting parameters that R is different from R square. So here he said for the first time, this number here, 3G minus 3, represents a complex dimension. And he introduced this structure, complex analytic structure. And so this paper is very short. In fact, it is more or less maybe 15 pages. There's a proof of this theorem, but said in very, a proof of this theorem said in very, it's in the style of Riemann. Riemann also, I mean, he had a proof of what he said, but you have to work hard for several years to understand what he's talking about. And 20 years after this theorem of this paper of Teichmuller, Grothendieck wrote a famous, in fact famous, but also not well known at all. In fact, many people, I mean, several people to whom I asked about this, especially algebraic geometers, never heard of these papers. So these are 10 papers in Cartan's seminar called. There are 10 papers. The title of the last one is Construction of Teichmuller Space, and the generic name is something like Construction Methods in Analytic Geometry or something like that. So he Grothendieck formulated the same theorem in his own words, and you see, and the Teichmuller space here, which is called T, is defined again by a universal property, which is the same universal property which Teichmuller talked about. And so we were wondering. In fact, we are a group of people working on these kind of things, including Vision G, Norbert Acampo, and some of my other colleagues. So, and we were wondering, why do people? In fact, there are several reasons why people did not read Teichmuller's papers. One of them is that these are really difficult to read, and I'm taking a quote here from one of the papers here, written, in fact, a note written by the editors of this journal, Deutsche Mathematik, and the editors say the following work is obviously unfinished. It has the character of a fragment. Unreasonably high demands are made on the reader's cooperation and imagination. For the assertions which are not even stated precisely with rigor, neither proofs nor even any clues are given. One thing not of fundamental importance, the residual elements occupy a broad space for something almost unintelligible, while far too scarce hints are provided for fundamental importance in the individual examples. But the author explained that he cannot do better in the foreseeable future. It will be, if we still publish the author's remark, despite all lag that distinguish the work against the other papers in this journal, it is to bring up for discussion the thoughts contained therein and relating to the theme of these fish functions. So this paper is one of his papers where he is making a discussion. In fact, it's a long paper, this one, maybe 30 or 35. There's a whole discussion on the relation with Riemann surfaces and Galois theory, the Galois theory of extensions of fields. And it is true that when you read this, I mean, sometimes you don't know what he's talking about. But I think that I mean, there are a lot of. I mean, these papers contain a lot of ideas. And this, I mean, I told you we are a group working on these papers. So this is, I finished now with my historical introduction, and I want to write on this blog. Yeah. In fact, is about, as Vanya said, it's about the arc metric metric on Teichmuller space. So I mentioned the complex structure of this space, but there's a lot of structure. In fact, this space carries a lot of structure. It carries metrics, several metrics. Probably the most famous one is the Teichmuller metric, which is explained in the longest paper of Teichmuller, paper of 175 pages long, where he studies this metric. He describes its geodesics. He shows that it's a Finsler metric. He asks several questions. He describes the tangent space of this Finsler structure as an equivalence class of Beltrami coefficients and so on. In fact, a very, very, very detailed description of this metric. This is his 1939 paper. And then there's another metric, which is the Weil-Petersen metric. And this is related to the papers of Grothendieck, which I mentioned. In fact, just before that, these Cartan seminars are from 1960, 1961. These 10 talks of, in fact, they are published. 10 talks of Grothendieck are 1960, 1961, and just a year before, André Weil gave us a Bourbaki seminar talk on Teichmuller's work, on part of his work, and then he noticed that it was André Weil who noticed that there's a kind of a product, not a scalar product, but a product on automorphic forms, which was defined a few years before by Petersen, which one could define on this, on the tangent and cotangent space of Teichmuller space. And in fact, one of the questions raised by Teichmuller in that paper was, is there a Kähler metric on this space? He asked explicitly the question, and the answer was given by André Weil, who defined this Kähler metric, which we call now the Weil-Petersen metric. So this is the second very important metric, and it has several implications. And I showed you the picture of Mirzakhani, and her main work is calculating volumes of, consisted in calculating volumes of the moduli space with respect to this Weil-Petersen metric. And then in fact, there are about 12 metrics which are studied everywhere in the literature. These are the main two, and there is a third one which I will talk. This is the first metric. I will talk a little bit about it. And the arc metric, is an analog of this first metric for surfaces with boundary. I have several co-authors here. Let me mention them. So this is Alessandrini, Weiss-Fusu, and Yamada. So different works with different people. So working on this arc metric. So let me recall you what is the first metric. So you have you have two, let's say two Riemann surfaces of genus G greater than 2. Suppose these surfaces are orientable and connected and without boundary for the time being, and without distinguished point. By the way, let me mention that in that paper of Teichmuller, the Riemann surfaces since the beginning are taken in all their generality. He starts by taking a Riemann surface with 6 or 7 parameters, because they could be orientable or not, they could have boundary or non-boundary, they could have special, distinguished point in the interior, they could have distinguished point on the boundary, and then he has a version where every point on the boundary is a distinguished point. So the maps that are used fix the boundary point-wise, so this is what we call the non-reduced Teichmuller space. So all these cases are considered since the 1930s. Anyhow, now let me take this Riemann surface of genus G, at least 2, and then I want to consider them as equipped with their Poincaré canonical metric. So by the uniformization theorem, I already mentioned Poincaré and his uniformization theorem. Any Riemann surface, any one-dimensional complex analytic, any complex analytic curve carries a canonical hyperbolic structure. So I will consider these. So this is my first Riemann surface, and this is the second one. And the Thurston metric tells you what is the distance. What is a distance? So t between this metric G and this metric H. So this is okay. There's a logarithm, and here there's a subprimum of the length for the metric H of, so alpha, let's say here, let's put it here, alpha belongs to this set S, and S is, well, set of isotropy classes of essential, that is not homotopy to a point, of essential simple closed curves. So you compare the length of curves for the metric H to the length of, so this, you are comparing lengths of the geodesics, the length of the shortest curves in the isotropy class. You are comparing the length of the shortest curve in each isotropy class. So here you have this geodesic, and here you have this geodesic. You see this one is a little bit shorter than this one. This one here is much shorter than its friend in this surface, and so on. So you are comparing the ratios of lengths of geodesics, and then you take the supremum and the logarithm. Of course, there's something to prove here. One of the things you have to prove is that this is always, if you want to have a measure of a distance, you want to prove that this is, when I put the logarithm, that this is always greater than 0, and that if the distance is 0, it means that the surfaces are the same, are isometric. This is one of the things you have to prove. And then one thing which you cannot prove and which is not correct, so it is not correct that this metric is symmetric. That is, the distance from G to H in general is different from the distance from H to G in general. In general, you have this inequation All the other axioms for a metric space hold except this one. But I mean, the thing which is proved, you know, by experience is that this is interesting. I mean, you can make definitions as many as you want. The important thing is that this definition leads to a reasonably difficult and sophisticated theory, and that you prove interesting theory. So even though this metric is not symmetric, it leads to a big quantity of very good results. For instance, I mean, with non-symmetric distances, you can ask the same questions as with symmetric distances exactly in the same way. You can talk about geodesics, you can talk about circles, you can talk about horocycles, you can talk about boundary structure, you can talk about perpendicularity theory, you can talk about parallelism, you can talk about boundaries. I mean, everything you can imagine for symmetric metric spaces, you can ask it for non-symmetric metrics like this one. It turns out that this, I mean, of course, you can symmetrize. You can define a distance, say, symmetric of g of h equals. There are several possibilities, but one of the two most obvious one is to take
You mean D?
Huh?
You mean D.
Pardon. No, thank you. Yes. Thank you. One of the obvious symmetrization is to take just the arithmetic symmetrization, and you can try to ask questions about this metric, but almost nothing at all is known about this metric. I mean, the whole theory developed by Thurston for this non-symmetric metric. You lose all the geometry. You use all the geometry for this. If you, I mean, this is of course, it's a good problem. I mean, if you have somebody has ideas on this metric, it would be very good. But for the moment, it's just a non-symmetric version, which is the useful one. There's another one which is a little bit better, for which there are some results, and this is you take the maximum of the two. It has a name, it's called the length spectrum metric. And it has been studied a little bit. I mean, there are some results on this length spectrum metric. There are some results, but nothing at all comparable with the theory which is developed for this non-symmetric metric. Let me now tell you what is the problem for surfaces with boundary, and why is there this arc metric? So now, if you want to apply this for surfaces with boundary, let's draw a surface with boundary. So this is a surface with boundary. So surface with geodesic boundary. Again, a hyperbolic surface. Then there's the following fact. In fact, let's call it a theorem. And this is G. Let's call it G. Well, for any G, for any such surface G, there exists another surface H, another hyperbolic structure H on the same topological surface, such that this, if you define this Thurston ratio here, if you take the same definition, is negative. So you cannot use the same definition unless you want to deal with metrics which take strictly negative values, and this is unreasonable. For the time being, this is unreasonable. Non-symmetric metrics which have this property here are, in fact, they were studied long ago by Guzman. He has several papers, and in his books there's a long discussion on non-symmetric metrics, and he kept telling that it's interesting to study non-symmetric metrics. And I'm sure that if Guzman knew this example of person, he would have been very happy, not only for this, but for several reasons in this theory of non-symmetric metrics. But of course, now at that time it was something not very fashionable. In fact, the whole thing of metric geometry was not so fashionable. Now it became fashionable, namely because of the good examples, and one of the good examples is this metric of person. So we have to modify. And if you are used to work with surfaces with boundary, then let me write it here, the modification. Okay, so instead of considering closed curves here for surfaces with boundary, I will consider this set B, which instead of the closed curve in the surface, you consider only the arcs joining boundary to boundary. So you compare distances of arcs. So this is an arc here, and you take this is the length of the shortest arc in this homotopy class, or in this isotopy class. And then you obtain something reasonable. You have exactly a non-symmetric metric like a Thurston's metric, and okay, you have a set of good results and good geometrical results. And let me explain to you at least one of these results. So first, let me go again to Thurston. Thurston's, which the thing he calls stretch lines. Let me just recall what it is. So I told you that there's a very good notion of geodesic for this metric, and there's in fact this distinguished class of geodesics. This metric here, I'm talking about this Thurston metric. There are several kinds of geodesics, in fact. A lot of geodesics which you can imagine. In fact, it's not very difficult to think about geodesics. In fact, you want this. You have to understand what is a geodesic here. Geodesic means that you have a line and 3 points, and then instead, for any 3 points on that line, the triangle inequality is an equality, and not an inequality. Not only an inequality, but an equality. This is the notion of geodesic for this kind of spaces. And of course, you have to take everything in the same order. A geodesic in general for such a space, if you traverse it in the opposite direction, is no more a geodesic. And of course now, again, since we are working with non-symmetric spaces, there are obvious questions, very good questions which appear and which do not appear in the symmetric case. For instance, describe a set of geodesics which are geodesics when you traverse them from the other side also. This is a question, an interesting question, which has partly solved here in this theory, and which is irrelevant in the case of symmetric metrics. And then there's this business of distinguished class of geodesics. So these stretch lines in First's theory, there's a distinguished class of geodesics. Not all the geodesics are stretch lines, but some of them. And here, also let me mention that Busemann thought about these kind of questions, and he has a book called Spaces with Distinguished Geodesics. That is, it says, like you can imagine as your metric space as embedded in a Euclidean space, for which the Euclidean lines are geodesics. So this solves kind of the Hilbert problem number 4. But there are other geodesics. But this class of Euclidean geodesics is a distinguished class of geodesics. So you can deal with both, either with all the geodesics or with the distinguished class. And all the good questions about geodesics, you can ask them either for all geodesics or the distinguished class. So let me tell you how Thurston defines these, how he constructs these classes of geodesics. So this is an ideal triangle. This is an ideal triangle in Lobachevsky plane, a triangle with 3 points at infinity, and then you have a foliation here, a foliation of this triangle. There's a central region here which is not foliated, but the rest is a foliation by pieces of horocycles perpendicular to the boundary. Okay? So this is the building block, and then you take another ideal triangle with same kind of foliation, and then you build a map from here to here, by taking it as the identity on the central regions, and where a piece of horocycle of a distance k from the center is sent to a piece of distance lambda k or e to the lambda k or something, whatever you want, and then you can vary this lambda. Varying this lambda gives you a one parameter maps between ideal triangles, and then you can glue the ideal triangles with each other in some way. You can glue them here. The ideal triangles are in your surface. For instance, you can imagine them as spiraling along this geodesic, but it could be more complicated. And then this gives you, when you glue them and you do this on each triangle, you do this operation on each triangle and you vary them, then you find a one parameter family of Riemann surfaces. This is your fixed Riemann surface, this is your variable Riemann surface, and then this map from here to here, where lambda varies, gives you a geodesic for Thurston's metric, which is called, he calls this a stretch line. And now let me just tell you for surfaces with boundary what you do. For surfaces with boundary, instead of these ideal triangles, you can take right-angled hexagons, so I take a pair of right-angled hexagons. I have to get used to this chalk. A pair of right-angled hexagons, and I want to take the symmetry. Symmetric means that here you have this distance L, here you have distance L, here you have distance L. The length is L, the length is the same for these three alternating sides, and of course by trigonometry, the lengths of the other three also are the same. And then here I want to take lambda L, and lambda L. I made a mistake somewhere. Here I take lambda less than 1 if you want this picture to be reasonable. And then you can vary lambda. You see, you can vary lambda, and then you have a foliation. You have a foliation which is now it's not a foliation by horocycles. It's a foliation by hypercycles, equidistant curves to the boundary. And then you have here a non-foliated region. You have here a non-foliated region. And then you the same kind of maps as there give you a family of maps between one fixed right-angled hexagon and a variable right-angled hexagon. And the right-angled hexagons, you can glue them and obtain a surface with boundary. You see, by cutting along a maximal system of geodesics. You see, these geodesics, they cut the surface in right angles, and when you cut a maximal system of such geodesic arcs, you get a right-angled hexagon. And so you obtain, these are geodesics for this arc metric, and one of the properties of these geodesics here is that you can double the surface, and obtain geodesics for the Thurston metric, for the initial Thurston metric, which has and these geodesics have the property, because of the symmetry here, that when you traverse them in the opposite direction, they are also geodesics. This is one of their interesting properties. And these are not stretched lines. These geodesics are not stretched lines. They belong to a class which is different from this class of distinguished geodesics. So I think I have to stop.
Thank you very much. So, questions? Comments? Well, I have one. Just to make sure, are you claiming that if you take arcs instead of closed geodesics,
yes,
here then you get positive?
Yeah, I have to add here the boundary component in order to be. Well, yeah.
Okay.
Then you get positive, and it is 0 if and only if the two surfaces are isolated. Yes, I can.
I see. More questions? So thanks. Thank you.